Okay, so show that the thermal energy removed from the gas for BC is approximately 330 joules, right? So here's the basis of our argument, right? The work done here is 0 because the piston doesn't move, the volume doesn't change. Remember that work is pressure change in volume, the change in volume is 0, so work is 0, okay? So that's concept 0. Concept 1 is that what Q is change in internal energy plus work. And we know that this is 0, okay? So the change in internal energy is going to be the heat removed from the gas. These guys are equal because work is 0, okay? So now the question is, how do you find the change in internal energy? That's fairly straightforward. The change in internal energy is going to be, since this is a monatomic, it's an ideal monatomic gas. Okay, so we can use this equation, right? I've never seen them use anything. So 3/2 nR delta T, right? Okay, so that's going to be, and then we know previously that the number of moles is 0.11797 moles. And we figured that out from knowing the pressure, the volume, and the temperature at A, okay? There's another way to do it, by the way, if you don't want to figure out the number of moles. Okay, and then I'll show you that. I'll show you that at the end, okay? So this guy is going to be 3/2 times 0.11797 times 8.31. And then our change in temperature is going to be, well, the final temperature is 385.54. By the way, they're going to use 386 because they told you that it was 386, and then we're going to go minus 612, right? Because we know this is 612 here. Remember that AB is isothermal, so this is 612 kelvins. This guy is 612 kelvins, right? This is isothermal, right? Same temperature. It's got the same thermal, right? So this is 612 to 385.535, okay? So let's do this. Let's do 3/2, 3 divided by 2, times the number of moles, times 8.31, times parentheses, that temperature that we just got, minus 612. And I get that the Q is negative 333.04 joules, right? So that's the heat removed. It's negative because the temperature dropped, okay? So that's one way to do it. There's another way to do this, though. Let me show you this, okay? Because U equals this, U also equals this. 3/2, and then we're going to say V delta P. And the reason we can do this is that PV is nRT, right? This side here is nRT, but it also can equal PV, right? So if only one of these changes, either the volume or the pressure, you can always do 3/2 either P delta V or V delta P, okay? So we can do this as well. So we can go delta U is 3/2, okay, times the volume, which is 3E minus 4. We know that because remember the volume here is twice the volume at A. And the volume at A is 1.5 times 10 to the minus 4th, right? And then the change in pressure is going to be 1.25991 E6 minus, and then the pressure here is going to be, well, this, okay, that's a little bit tricky, right? So the pressure here was 4 E6, right? If you double the volume, the pressure here is going to be 2 E6. And they make the graph, like this is not the origin, right? Okay, which is kind of stinky of them, I think. Okay, so 2 E6. Okay, so we're going to go 3 divided by 2 times 3E minus 4 times left parenthesis, that pressure right there, minus 2 E6. And indeed, I get exactly the same number because, of course, these numbers come from each other, right? I get that the delta U, which is equal to the Q, is equal to negative 333.035 joules. All right. Woohoo!